Assalamualaikum warahmatullahi ta'ala wabarakatuh. We are from Group 12 are going to present about student stress level prediction using various data mining techniques. We have 3 team members including Anissa Sofia, me, Shamirahani and Nurul Husna.
For our project, we use the data set from Kaggle, where the title of the data set is the student stress and performance insight. It provides the insight into the student lifestyle, pattern, and their relationship with the stress level and academic performance.
Data mining techniques such as classifications, clustering, and also statistical analysis. So classification is a technique used to predict categories or level. For example, if you want to predict if a person is stressed or not stressed. So the stress or not stress is the levels. And for clustering is a technique which groups similar data points together based on their characteristics, such as if we want to grouping the people with similar stress behavior. While statistical analysis is a technique we describe the data using numbers, such as if we want to calculate the average stress score, or we want to check is the longer working hours will increase the stress or not. So based on these data sets, we choose classification as the most suitable data mining techniques due to we want to predict the students either stressed or not stressed. So this is the classification algorithm, which is we have 3. First is random forest, support vector machine SVM, and then third one is k nearest neighbors KNN. So what is random forest is a learning algorithm that builds multiple decision trees and combine their output to make an accurate predictions, while SVM is algorithm where we want to find an optimal line, or we call it as hyperplane, that separates the classes. So we want to maximize the distance of hyperplane. And k nearest neighbors is by using proximity to make the classification. So the similar points are close to each other. We classify it as the new point based on its neighbors. Evaluation of using those 3 algorithms, I have compared ROC curve, accuracy, and classification reports to evaluate those 3 algorithms. So with using random forest, it shows us 100% accuracy, 94.5% accuracy using SVM, and also 92.25% accuracy using KNN. So the best one is using random forest, followed by SVM and KNN. With random forest, it shows us very high potentials, highest potential with the 100% accuracy of the evaluations. Random forest, it's good at handles large data sets. It handles missing value or outliers, and also it helps us to provide or to show the most important features and minimizing the overfitting. However, if we use random forest, it is slower if we use for large data sets. It is hard to interpret the data sets compared to using a simple decision tree. So with random forest, we can use it in automated stress alerts, where it sends the notification or alerts to the students who has higher stress level, and it helps schools or organization to prioritize which students need their help, and also can guide policy or workplace adjustment by analyze stress trigger when we use random forest. SVM shows us high potentials with 94.5 accuracy. The benefits or the strengths of SVM is it is work very well with high dimensional data. It is more effective when we have more features numbers compared to the samples numbers, and also provide us with good generalizations. However, it doesn't perform well if the data is unbalanced or noisy, and it's a bit hard to tune and interpret, and it works slower with using very big data sets. So SVM is useful for predicting stress or burnout with higher accuracy, and it is suitable for using at the environments like hospitals or therapy sessions. And it also provides professionals like therapists to have a reliable for one-on-one stress counseling decision based on their predictions using SVM. In KNN, it shows us moderate potentials with the 92.25 accuracy compared to the SVM and random forest. The strength of the benefits of using KNN is it is very simple. There is no training phase. It just store the data, and it works very well with small data sets. However, if we use big data, it will give us slow prediction time. It is sensitive to the noisy data and different scales of features, and it's not ideal for imbalanced classes. If you're using KNN, it is best for simple prototype or apps like basic stress check tools that it will help us in giving early awareness of higher stress level.
Before we could build a model to predict a student stress level, the first major step is the data processing. Processing is essential because real-world data is often messy and inconsistent. If we don't clean and prepare the data properly, the model will produce poor and misleading results. In our project, we follow a several processing steps to make the data ready for a machine learning. The first one is the handling missing value. The data set had some missing entry, for example, missing sleep hour or academic score. We handle this by removing rows that had too many missing values, or the others we fill them using the mean for numerical feature and the mode for the categorical feature. This helped bias and ensure every record was usable. But for our dataset, the result shows that there is no missing value. The second one is Z score filtering. The dataset had some extreme value, for example, 0 hours for sleep or 100 study hours. We handle this by applying Z0 filtering to identify and remove outliers. We calculate the Z0 to measure how far each data point is from the mean in terms of the standard deviation. And the last one is we using the normalization and scaling. We noticed that some features like study hours and academic score had very different range. To make sure all the features contribute equally to the model, we apply mix and match scaling to bring the value into the same scale. Next is the feature selection. The feature selection is all about the choosing the most important variable that have a strong influence on the target variable. For our project, we use 5 features where the result conclude that only one feature that more important. And for our project, we use a few techniques to get the result. The first one is the correlation analysis to check how each feature is related to the stress level. Next one is chi-square test. Chi-square test is for the categorical variable such as a parental support or availability of resource. This statistical test measure the dependency between the categorical feature and the stress level. The last one is the ANOVA, analysis of variance. The ANOVA used to assess the impact of the numerical feature like study hours and physical activity on the stress level. Pre-processing and feature selection are not just technically tasks, they directly improve how well the model works and how useful it is in practice. Let's take a look at the real-world impact this had on our project success. First is the accuracy. By removing the missing value and calling the variable properly and selecting only the most relevant feature, our model had less noise and irrelevant data to learn. Second is reliability. With a clean and consistent dataset, the model is more stable, where it gives more consistent results even when the test with the different sample. And the last one is the interpretability, where the feature selection helps us in identifying which factors truly affect the student stress, like lack of the sleep, long study hours, and family pressure.
Stakeholder trust and adoption. To ensure stakeholders view the stress prediction model as a reliable and worthy for adoption, we took 3 key steps. Firstly, we used a transparent and interpretable model called random forest, which allowed us to extract feature importance scores. This provided clarity on how different factors like sleep hours or physical activity influence the prediction. We implemented this using feature importance from the trained model, helping explain the model's logic in simple terms. Secondly, we validated the model using evaluation metrics, including accuracy and ROC AUC score, which we calculated and presented through our test.py script. These metrics demonstrated the model's reliability and strong performance in classifying stress levels. Lastly, we emphasized the importance of stakeholder involvement. Although this part was theoretical, we aligned our approach with practical needs by tailoring the dataset to relevant academic lifestyle features and designing the system with educational stakeholders in mind, such as counselors and lecturers who could use this information to intervene or support students. Ethical considerations. During implementation, we addressed several ethical concerns to promote fairness and responsibility. Firstly, we tackled bias by analyzing the subjectivity and self-reported stress levels. In a file named feature.py, we used random forest model to help us detect if there is any data imbalance. For example, if a feature is to be revealed to contribute 80% to an output, this is a red flag since this dataset expects multiple other influencing features. Secondly, we consider individual privacy by ensuring that the dataset contains no personally identifiable information and by handling all data locally within a controlled environment without exposing it online. Lastly, we aim to avoid harm by positioning the model as a support tool, not a judgment system. The intention was for educators to use predictions to identify students who may need mental health resources and not to penalize them or label them unfairly. Potential challenges. We encountered 3 primary challenges in handling this dataset. Firstly, it was that stress level was self-reported and highly subjective. This variability introduced noise, weakening the reliability of feature-to-output relationships. We acknowledge this challenge in our presentation as a key limitation of working with survey-based mental health data. Next is the inaccuracy or missing data issue. As our dataset was sourced from surveys, the responses is highly dependent on each student's honesty and understanding of the question. We addressed this by using preprocessed.py to remove any rows containing missing values. However, we still recognize that remaining inaccuracy still pose risks to the model's learning process. Lastly, there is no external validation source. Without a medical or psychological benchmark to confirm stress levels, we couldn't verify the accuracy of self-reported responses. This limited our ability to fully validate the model's real-world correctness, which we acknowledge when evaluating its application in a practical setting. In conclusion, this report has explored the applications of various data mining techniques, particularly classification, clustering, and statistical analysis, in predicting student stress levels based on lifestyle patterns. While classification emerged as the most suitable method for our dataset, each technique demonstrated distinct strengths and limitations that influence how insights are interpreted and applied in educational domain. Additionally, we emphasize the vital role of pre-processing and feature selection in enhancing model accuracy, reliability, and clarity, especially when working with survey-based data. Now, to ensure stakeholder trust and successful adoption, we outline steps such as transparent modeling, validation practices, and collaborative involvement, while also recognizing key ethical concerns including bias, privacy, and potential for harm. Together, these considerations form a comprehensive foundation for building predictive systems that are not only effective, but also responsible and align with real-world needs in education. That is all from us, Group 12. Thank you.